In this video, we are going to study about the solubility of organic compounds in 5% sodium hydroxide, 5% sodium bicarbonate, 5% HCl, and concentrated sulfuric acid. Now, let's look at 5% sodium hydroxide and 5% sodium bicarbonate. Sodium hydroxide is a strong base, and sodium bicarbonate is a relatively weak base. So, sodium hydroxide can dissolve strong acids as well as weak acids because it's a strong base. So, it can dissolve both. When you come to sodium bicarbonate, being a weak base, it can dissolve only strong acids. It cannot dissolve weak acids. So, in organic chemistry, carboxylic acids are strong acids. COOH is a strong acid. Phenols are weak acid. A benzene ring with a OH is a phenol, and this is a weak acid. So, we can see that sodium hydroxide will be able to dissolve, say, benzoic acid, which is a carboxylic acid, and phenol, whereas sodium bicarbonate will dissolve benzoic acid but may not dissolve phenol because phenol is not a strong enough acid to succumb to sodium bicarbonate. Okay. So the reactions that happen are as follows. You have RCOOH plus sodium hydroxide. It will form the sodium salt RCO minus Na plus water. And if you have sodium bicarbonate, then that will give RCO minus Na plus carbon dioxide plus water. We saw that the carboxylic acid functionality can impart or favor acidity. Once again, depending on the nature of R, the acidity can decrease or increase. If R is electron withdrawing, then it would increase the acidity. And if R is electron donating, then that would decrease the acidity. Because electron withdrawing group can easily remove the proton here, and electron donating group will decrease the ability to remove the proton. Consider phenol. We said that phenol is a weak acid. We can increase the acidity of phenol by adding electron withdrawing groups like nitro group in the ortho or para position. So this is orthonitrophenol, and this is more acidic than phenol. If we add more nitro groups in the ortho position, then the acidity is increased even further. So this is 1, 2, 3, 4, 5, 6. So this is 2,6 dinitrophenol, and this is more acidic than 2-nitrophenol. If we add one more nitro group and put it in the para position, then we get 2,4,6 trinitrophenol, which is more acidic than the dinitrophenol. So we can see how we can increase the acidity by using electron withdrawing groups in the appropriate positions. And 2,4,6 trinitrophenol, as opposed to phenol, is actually soluble in NaHCO3. Okay, now let's see about the solubility in HCl and concentrated sulfuric acid. Amines, being basic, are soluble in HCl. So amines are NH2 groups, and these are basic in nature. So you can have a primary amine, or you can have a secondary amine, or we can have tertiary amine, and they're all basic, and they all react with HCl to form salts. So RNH2 plus HCl will give us RNH3 plus Cl minus. Again, depending on the nature of R, if the hydrocarbon is large and more hydrophobic, that can decrease its ability to react with HCl and form salts. Coming to concentrated sulfuric acid. Concentrated sulfuric acid can react with aldehydes, ketones, alcohols, esters. Concentrated sulfuric acid can protonate the oxygen, making esters, acids, alcohols, and ketones and aldehydes soluble.